Hello there, and welcome to the Sleeping Physicist. If you are someone who enjoys unwinding by thinking about particles, forces, and the quiet structure underlying the universe, you are in the right place. Here, we let our attention settle into real physics and real discoveries, taken slowly and carefully. Some ideas may feel surprising at first, but everything you hear is grounded in what experiments and theory have patiently revealed about nature. And if you find yourself enjoying these unhurried explorations, you are welcome to like and subscribe. For now, allow yourself to settle in. Let the day loosen its hold. Let curiosity take the lead. And let us begin. What is a charge made of according to quantum physics? In the everyday world, charge first appears through simple effects. A balloon sticks to a wall. A spark jumps from your finger. Light objects lift and drift without being touched. In each case, nothing visible moves between the objects, yet something has clearly changed. The space around them behaves differently, as if it has gained a new tendency to pull or to push. What matters here is that charge shows itself as influence rather than substance. Two charged objects respond to one another across empty space. They do not need contact. They do not exchange anything we can see. This tells us something immediately important. Charge is not acting like a material that flows or piles up. It is acting like a property that reshapes how objects relate through space. If charge were made of tiny pieces of stuff, we would expect it to clump or leak away. We would expect wear and loss. Instead, charge remains stable. An object either has it or does not. When charge changes, it does so in a controlled and repeatable way. This steadiness points away from charge as material and toward charge as a basic feature of nature. So from the very beginning, observation guides us gently. To ask what charge is made of may already be slightly misframed. The behavior of charged objects suggests that charge is not built from smaller ingredients. It is something more elemental, a property that determines how matter participates in the electromagnetic structure of the universe. This way of thinking did not arrive all at once. Early physics treated charge as something closer to a fluid. It was imagined as a subtle substance that could move from place to place. Objects were thought to gain or lose it the way a container gains or loses water. This picture felt natural because it matched everyday experience with materials. But careful experiments began to strain that idea. Charge did not behave like a fluid that thins out when spread. It did not weaken with use. It did not smear across space. When scientists measured electrical effects with increasing precision, they found the same amount of charge appearing again and again. It showed no signs of being divisible at will. This led to a quiet but profound shift. Charge began to be treated not as a thing an object carries, but as a property an object has. Much like mass or length, it became something intrinsic, a stable attribute that defines how an object behaves rather than something stored inside it. Once this change took hold, the behavior of electricity made more sense. Objects did not exchange charge the way buckets exchange water. Instead, interactions rearranged which objects possessed the property. The property itself remained intact. Nothing was used up. Nothing was diluted. This shift matters because it clears the ground for quantum physics. If charge is not a substance, then asking what it is made of becomes a different kind of question. We are no longer looking for smaller pieces. We are preparing to look for deeper rules, rules that determine why certain particles have this property at all. As experiments grew more refined, attention turned to the smallest pieces of matter that could still carry this strange property. Atoms were no longer indivisible. Inside them lived smaller components, and two of them stood out immediately: the electron and the proton. Again and again, charge appeared attached to these particles with unwavering consistency. Electrons always carried the same negative charge. Protons always carried the same positive charge. No experiment ever found half an electron charge or a slightly stronger proton charge. This regularity was striking. It suggested that charge was not something these particles picked up along the way. It was something bound to their very identity. This was the first time charge felt anchored, not to materials or surfaces, but to specific particles. When objects became charged, what actually changed was the arrangement of electrons. Some objects gained extra electrons, others lost them. Protons remained locked inside atomic nuclei, stable and inaccessible in everyday processes. This realization simplified the picture. Electrical phenomena were no longer mysterious fluids or invisible vapors. They were the result of counting how many electrons were present, where they were allowed to move, and how strongly they responded when nearby charges were rearranged. Yet this clarity raised a deeper question. If electrons and protons always carry the same charge and never vary, then charge is not something built inside them from smaller pieces. It arrives whole, complete, attached, without explanation. And that quiet fact begins to point us toward the quantum description that comes next. Once electrons and protons were identified as the carriers of charge, measurements became sharper. Scientists expected that with enough precision, charge might vary smoothly, a little more here, a little less there. But nature refused to cooperate with that expectation. Every experiment pointed to the same result. Charge always appeared in exact units. An electron carried one negative unit. A proton carried one positive unit. Nothing in between ever showed up. No fractions, no gradual scale. Charge behaved like a countable feature rather than a continuous one. This was deeply unsettling at first. Many physical quantities vary smoothly. Length can be any value. Energy often comes in ranges, but charge arrived in steps, always the same step size, as if nature had decided on a smallest possible amount and refused to go below it. The simplest way to see this is through accumulation. When an object gains charge, it does so by gaining whole electrons. When it loses charge, it loses whole electrons. No process ever transfers half an electron. No experiment has ever detected a smaller free unit of charge. This discovery quietly reshaped the question again. If charge comes only in fixed units, then it is not assembled from smaller components. It is not granular because it is built from pieces. It is granular because it is fundamental, like a letter of an alphabet, rather than a word made of syllables. And with that realization, the path forward becomes clearer. To understand what charge is made of, we must stop searching for ingredients. Instead, we must begin asking what rules of nature make such fixed properties possible at all. At this point, a pattern becomes impossible to ignore. Charge does not behave like something assembled. It does not reveal layers when examined more closely. Instead, it behaves like a label written into the fabric of particles themselves. In physics, a fundamental property is one that does not come from anything simpler. Mass is one example. Spin is another. These are not made of parts. They are attributes that particles simply possess. Charge joins this category. It is not constructed. It is assigned by the rules of nature. This means the question changes shape. Asking what charge is made of no longer makes sense in the usual way. There is no internal machinery inside an electron that produces charge. There is no hidden structure that can be taken apart. The charge is the property. It arrives whole. An analogy can help here. Consider a chess piece. A bishop is not made of diagonal movement. It is defined by it. The rule comes first. The behavior follows. In the same way, charge is a rule that determines how a particle behaves when other charges or fields are present. Once this is accepted, many puzzles dissolve. The fixed size of charge units makes sense. Their perfect stability makes sense. There is nothing inside charge that can erode or decay. It is not a substance that can leak away. It is a rule that remains intact as long as the particle exists. And this realization opens the door to the next layer of understanding. If charge is a fundamental property, then it must be tied to something even deeper than particles themselves, something that tells particles how to exist and how to interact. To reach that layer, physics takes a decisive step beyond particles and into fields. Once charge is understood as a fundamental property, particles themselves begin to look less like tiny objects and more like expressions of something deeper. This is where modern physics takes a decisive turn. The focus shifts away from particles as primary and toward fields as the underlying reality. In quantum physics, a field is not an abstract bookkeeping device. It is a real physical presence that exists everywhere in space. Even in regions we would casually call empty, fields remain. They do not switch off. They do not thin out. They form the background structure of the universe. Particles emerge from these fields. An electron is not a tiny bead moving through emptiness. It is a localized excitation of the electron field. Much like a ripple rising on the surface of a calm lake, the particle is the visible expression. The field is what makes it possible. This change in perspective is profound. If particles are excitations of fields, then their properties come from the fields they arise from. Charge is no longer something a particle carries around. It is something defined by how that field interacts with another field. The electromagnetic field fills all of space. It is responsible for electric and magnetic effects. When a particle has electric charge, what that truly means is that its field is linked to the electromagnetic field. The two respond to one another. They are allowed to interact. An analogy helps clarify this without replacing the physics. Imagine a dancer moving across a floor. The dancer is visible, the music is not. But the movement only makes sense because the music is there. In the same way, particles move and interact because fields exist beneath them. Charge is not the dancer. Charge is the rule that connects the motion to the music. This framing explains why charge feels so stable. Fields are fundamental. They do not wear out. They do not fragment. As long as the field exists, its allowed interactions remain fixed. That is why every electron has the same charge. They are all excitations of the same field, obeying the same rules. It also explains why charge is not something we can peel apart. There is no smaller component hiding inside it. Charge is a relationship written into the structure of fields themselves. A permission, a coupling, a way that one field is allowed to respond to another. From this viewpoint, the original question begins to settle. Asking what charge is made of is like asking what a rule is made of. The rule is not assembled, it is defined. And once defined, it shapes everything that follows. This brings us naturally to the next step. If charge is a relationship between fields, then understanding charge means understanding how strongly those fields are linked. Not all couplings are equal. Some are weak, some are strong. And in quantum physics, that strength carries deep meaning. Once fields take center stage, charge reveals its true role. It is not a substance inside a particle. It is not an object attached to it. Charge is the measure of how a particle's field is allowed to connect to the electromagnetic field that fills all of space. In quantum physics, this connection is called a coupling. The word sounds technical, but the idea is simple. A coupling tells us whether two fields can influence one another and how strongly they do so. If a particle has electric charge, its field is coupled to the electromagnetic field. If it has no charge, that coupling is absent. This explains something that once felt mysterious. Why does an electron respond to electric and magnetic fields while a neutrino passes through almost untouched? The answer is not hidden inside the particles. It lies in which fields are linked by the rules of nature. The electron field is connected to the electromagnetic field. The neutrino field is not. Charge, then, is not an ingredient. It is a permission. It tells the universe that when an electromagnetic field is present, this particle must respond. It tells the electromagnetic field that when this particle exists, it can feel its presence. The interaction goes both ways. An analogy can help make this intuitive. Imagine two people in separate rooms connected by a thin wall. If the wall allows sound to pass, they can hear each other. If the wall blocks sound, they remain isolated. Charge is like the openness of that wall. It determines whether interaction is possible at all. This also explains why charged particles influence space around them even when nothing is nearby. A charged particle modifies the electromagnetic field around it simply by existing. The field adjusts. That adjustment can later affect other charged particles that enter the region. No message is sent. No substance travels ahead of time. The field itself carries the structure of the interaction. Seen this way, electric forces are not mysterious, actions at a distance. They are local responses of a field that is already there. Charge tells the field how to respond. The field tells other charges what to do. Everything unfolds continuously through space. This perspective also clarifies why charge never fades. As long as the field exists and the coupling rule remains the same, the interaction strength does not change. The electron does not slowly lose its charge because the coupling is not a stored resource. It is a fixed relationship defined by the structure of the theory. So when we ask what charge is made of, the answer continues to sharpen. Charge is not built from parts. It is not hidden matter. It is the strength of a connection between fields, a number that tells nature how interaction is allowed to happen. And this naturally leads us forward. If charge is a coupling, then its value matters deeply. Why this strength and not another? Why all electrons share it exactly? To explore that, we must look more closely at what coupling strength really means in quantum field theory. In quantum field theory, coupling strength is not a metaphor. It is a precise statement about how strongly two fields influence one another whenever they meet. For electric charge, this strength determines how intensely a particle responds to the electromagnetic field. A stronger coupling means a stronger reaction. A weaker coupling means the field barely notices the particle at all. This is why charged particles accelerate in electric fields, radiate energy, and exert forces on one another. The coupling sets the scale of all these effects. What is striking is that this strength is not negotiable. The electron does not choose how strongly it couples. The value is fixed. Every electron everywhere responds in exactly the same way. This tells us that charge is not something learned or acquired. It is written directly into the structure of the field. In quantum field theory, couplings appear as constants. They are not built from simpler quantities. They are inputs to the theory itself. This can feel unsatisfying at first. We often expect deeper explanations to reduce complexity. Here, depth arrives as acceptance. Some numbers are not explained by smaller numbers. They are part of the foundation. An analogy can help clarify this point. Imagine a rule book for a game. Some rules explain others, but eventually you reach rules that are simply declared. They are not derived. They define how the game works. Coupling strengths play a similar role in physics. They define how fields are allowed to interact. This does not mean the values are meaningless. On the contrary, they shape everything: the size of atoms, the behavior of chemistry, the stability of matter itself. If the electric coupling were slightly stronger, electrons would bind more tightly. If it were weaker, atoms might never form stable structures at all. There is also subtlety here. In quantum field theory, interactions can change slightly depending on energy. This is known as running coupling. At higher energies, the effective strength of interactions can shift, yet even this behavior follows precise rules. The underlying coupling still exists. It simply reveals different aspects of itself at different scales. What matters for charge is that its existence and its strength are inseparable. To have charge at all is to have a defined way of interacting with the electromagnetic field. There is no charge without coupling. There is no coupling without a specific strength. So the question continues to transform. Charge is not made of anything smaller. It is a number that governs interaction, a rule that determines response, a strength that shapes the behavior of matter across the universe. And with this understanding, another realization becomes unavoidable. If coupling strength defines interaction, then the field it couples to must be just as real as the particles we observe. To fully understand charge, we must now turn our attention to the electromagnetic field itself. Once coupling strength is understood, the electromagnetic field itself can no longer be treated as a mathematical convenience. It must be taken seriously as something physically real, not a background, not a placeholder, a genuine component of the universe that exists everywhere, even where nothing else seems to be present. Empty space, in this view, is not empty at all. It is permeated by the electromagnetic field at every point. This field can store energy, it can change shape, it can carry influence from one place to another. When nothing appears to be happening, the field is still there, quietly structured and ready to respond. This is why charge does not need to send signals outward. A charged particle does not reach across space to affect another one. Instead, it locally alters the electromagnetic field around it. That alteration spreads through the field. When another charged particle enters that region, it responds to the field as it finds it. This shift dissolves the idea of action at a distance. Nothing leaps across emptiness. Everything happens through continuous local change. The electromagnetic field acts as the medium through which all electric and magnetic effects unfold. An analogy can help anchor this intuition. Imagine a stretched fabric laid across a frame. Pressing down in one spot changes the shape of the fabric nearby. That change extends outward. Any object placed on the fabric later will feel the altered shape. The fabric was always there. The interaction happens through it, not across it. The electromagnetic field behaves in this way, though far more precisely and subtly. A charged particle reshapes the field configuration around it. That reshaping defines forces, energy flow, and motion. The field is not reacting passively. It is actively participating. This explains why electromagnetic waves exist. Light itself is a vibration of the electromagnetic field. No particles are required to carry it through space. The field oscillates on its own, transporting energy and momentum across vast distances. Once this is accepted, charge becomes even clearer. Charge is not something sitting inside a particle waiting to act. It is the rule that determines how a particle modifies the electromagnetic field and how it responds to changes in that field. This also explains why uncharged particles can pass through electromagnetic environments with little effect. Their fields simply do not couple. The electromagnetic field remains largely indifferent to their presence. So when we ask what charge is made of, the answer continues to simplify. Charge is not built from material pieces. It is not hidden structure. It is a defined way of participating in a real, physical field that fills the universe. And from here, the picture becomes more dynamic. If the electromagnetic field is real and active, then interactions must involve something moving within it. Not objects, not substances, exchanges. To understand how charge actually mediates forces, we must now look at how the field communicates change through quantum interactions. Once the electromagnetic field is taken seriously as something real, interaction begins to look less like force and more like communication. Not messages sent across space, but continuous local adjustments unfolding moment by moment. When two charged particles influence one another, nothing travels between them in the ordinary sense. There is no tiny object fired from one to the other. Instead, the electromagnetic field between them is constantly responding. Quantum physics gives this process a name. It calls these responses virtual photons. Despite the name, virtual photons are not particles you could ever catch or isolate. They are not flashes of light moving through space. They are temporary disturbances in the electromagnetic field, brief shifts that allow charged particles to sense one another's presence. This interaction is always happening. Even when particles appear still, the field between them is active. It is adjusting. It is exchanging influence. What matters is not the objects themselves, but the process. A charged particle modifies the electromagnetic field around it. That modification propagates outward. When another charged particle enters that region, it responds to the altered field. The response then feeds back into the field again. This loop continues without pause. Nothing is ever thrown across space. Nothing jumps instantaneously. Everything happens locally, step by step, through the field that already exists. This makes charge feel less like possession and more like participation. To have charge is to be involved in this ongoing exchange, to be unable to avoid shaping the field and being shaped by it in return. Virtual photons are not optional. They are the mechanism by which the coupling we discussed earlier actually operates. Without them, charge would be a number with no effect. With them, charge becomes active, dynamic, alive within the field. This also explains why electromagnetic forces can be both attractive and repulsive. The direction of the field response depends on the sign of the charge. The same mechanism produces both behaviors. The difference lies in how the field adjusts when charges are present. Importantly, this exchange does not drain anything. Virtual photons are not spent. The field does not run out of influence. Interaction does not consume charge. It simply expresses it. Here, the original question grows quieter. Asking what charge is made of feels less pressing. What matters more is what charge does. It sets the terms for this constant field-mediated conversation. It defines how strongly and in what way a particle must participate. And this brings us closer to something deeper still. If these interactions are governed by precise rules, and if charge determines how fields respond, then there must be a deeper principle deciding which interactions are allowed at all. That principle is symmetry, and it will quietly reshape how we understand why charge exists in the first place. At this stage, it becomes natural to ask why charge never fractures. Many properties in physics reveal structure when examined closely. Matter breaks into atoms. Atoms break into particles. Energy splits into quanta. Yet charge remains stubbornly whole. No experiment has ever observed a charged particle shedding part of its charge. An electron cannot lose a fraction and remain an electron. A proton cannot split its charge across time or space. Charge either exists in full or not at all. The reason lies in what charge truly is. Charge is not stored inside a particle like material inside a container. It is not assembled from components that could be separated. It is a rule governing interaction. Rules do not fragment. In quantum field theory, particles are defined by the fields they arise from, and the symmetries those fields obey. Charge is one of those defining features. Remove it, and the particle ceases to be the same entity. There is no internal mechanism to dismantle. Charge is not supported by substructure. It is supported by consistency. the consistency of the field and the rules that govern it. This also explains why charge remains identical across the universe. An electron here and an electron billions of light years away behave the same way. They respond to electromagnetic fields with identical strength. They generate identical field disturbances. Nothing about location or history alters this. The universe enforces this sameness because the underlying rules are the same everywhere. Fields do not locally rewrite their own properties. Symmetry demands uniformity, and charge is an expression of that demand. There is another quiet implication here. If charge could break down, interactions would become unstable, forces would drift, atoms would slowly change their behavior, chemistry would erode over time. None of this happens. The stability of matter depends directly on the indivisibility of charge. So charge remains whole not because it is protected, but because it is not made of parts to begin with. It is not something that can be chipped away. It is a condition of participation in electromagnetic interaction. Seen this way, the indivisibility of charge stops being mysterious. It becomes inevitable. You cannot partially follow a rule. You either follow it or you do not. A field either couples or it does not. This brings us closer to the deepest layer of the explanation. If charge exists as a rule and remains conserved and indivisible, then something must be enforcing that rule across all interactions. That enforcement comes from symmetry, not as an aesthetic idea, but as a physical requirement built into the structure of the universe. And once symmetry enters the picture, charge begins to look less like a property particles happen to have, and more like a consequence of how reality is allowed to be arranged at all. To understand why charge exists, physics steps into symmetry. Not symmetry as decoration, but symmetry as a strict rule about what can change and what must remain the same. In quantum field theory, certain transformations leave the laws of physics untouched. You can shift a field's internal phase everywhere in space, and nothing observable changes. The equations still work. The predictions remain identical. This quiet invariance is called gauge symmetry. At first, it sounds abstract, but its consequences are concrete. When a theory has this kind of symmetry, nature demands something in return. It requires a field that keeps the symmetry intact at every point in space and time. For electromagnetism, that required field is the electromagnetic field itself. Charge enters here, not as an added feature, but as a necessity. If a particle's field respects this symmetry, then it must interact with the electromagnetic field in a very specific way. That interaction shows up as electric charge. In other words, charge is not an optional property particles happen to carry. It is the mark of a field that participates in a symmetric structure. Remove the symmetry, and charge disappears. Enforce the symmetry, and charge must exist. This reframes the entire question. Charge is not invented by particles. Particles inherit charge because the underlying rules allow only certain kinds of fields to exist. Those fields come with required interactions. Charge is one of them. What makes this powerful is how restrictive it is. Gauge symmetry does not allow half measures. Either a field transforms in the right way and couples to the electromagnetic field, or it does not. There is no gradual entry, no adjustable participation. This explains why charge values are so precise. The symmetry fixes the form of the interaction. Once fixed, the coupling cannot drift without breaking the symmetry itself. Nature does not permit that break, because the entire structure of the theory depends on the symmetry holding everywhere. It also explains why different particles can share the same charge. They may be very different excitations arising from different fields, but if they transform under the same symmetry in the same way, their charge must match exactly. Seen this way, charge stops looking mysterious. It is not a substance waiting to be discovered. It is a consequence. a footprint left behind by a deeper requirement that the laws of physics remain unchanged under specific transformations. This is one of the quiet triumphs of modern physics. Instead of asking why charge exists and receiving no answer, the question is inverted. Given the symmetry of the universe, how could charge not exist? And this brings with it another powerful result. If charge arises from symmetry, then it cannot be created or destroyed arbitrarily. Symmetry does not allow that. From this same principle emerges one of the most reliable rules we have ever observed, the conservation of charge. That rule will carry us forward next, because it reveals how deeply charge is woven into every interaction that occurs, from the smallest particle process to the largest cosmic structure. Once symmetry enters the story, conservation follows with quiet certainty. Conservation of charge is not an added rule layered on top of physics. It is a direct consequence of the symmetry that gives rise to charge in the first place. In every experiment ever performed, charge is conserved. It can move, it can be rearranged, it can appear in new particles and disappear from others. But the total amount never changes. Nature keeps perfect accounting. This is not because charge is carefully guarded. It is because the symmetry does not allow imbalance. The same gauge symmetry that requires the electromagnetic field also forbids the creation or destruction of net charge. To violate conservation would be to break the symmetry itself. When particles interact, charge does not vanish into nothingness. It is transferred. When an electron is emitted, something else gains the opposite charge or adjusts accordingly. The field ensures that the overall balance remains exact. This holds even in the most extreme situations. In high-energy particle collisions, particles are created and annihilated. Matter turns into energy. Energy condenses back into matter. Through all of this, charge remains steady. It is redistributed with precision, never lost. This persistence is not enforced by a mechanism acting in time. It is enforced by structure. The equations themselves do not permit an outcome where charge simply disappears. The symmetry closes that door completely. This gives conservation of charge a different feeling than conservation of energy or momentum. Those feel intuitive because they connect to motion and work. Charge conservation feels quieter, more absolute. It is not about balance after the fact. It is about what outcomes are even allowed to occur. There is an important implication here. If charge is conserved because of symmetry, then its stability does not depend on conditions. Temperature does not matter. Density does not matter. Cosmic time does not matter. As long as the symmetry holds, charge conservation holds. This is why the same rules apply everywhere, in the heart of a star, in a laboratory, in the early universe. The electromagnetic symmetry does not weaken with distance or age, and so charge remains conserved across all of space and time. From this perspective, charge begins to feel less like a property particles carry, and more like a constraint the universe obeys. Particles do not decide how much charge to have. Interactions do not negotiate it. The symmetry defines what is permitted, and everything else follows. This also explains why conservation of charge has never been violated, even accidentally. It is not something that could fail under the right conditions. There are no right conditions for breaking a symmetry that is built into the framework itself. So when we ask what charge is made of, conservation gives a quiet answer. Charge is made of consistency, of invariance, of rules that do not bend. And once conservation is understood, this way another question naturally emerges. If charge is conserved and fundamental, how exactly does it influence how particles move and respond when fields are present? To answer that, we must look at how charge determines a particle's behavior inside electromagnetic fields themselves. Once conservation is understood, charge takes on a more active role. It is not just something that must be preserved, it is something that directly shapes motion. Whenever an electromagnetic field is present, charge decides how a particle will respond. An uncharged particle can move through an electromagnetic field almost as if it were not there. Its path is largely unaffected. But a charged particle cannot ignore the field. The presence of charge means the particle must respond. Its motion bends, its energy changes, its trajectory becomes linked to the structure of the field around it. This response is not delayed or negotiated. It is immediate and local. At every moment, the particle feels the field at its exact position. The field pushes or pulls according to the charge it encounters. This is why electric forces feel so direct. There is no memory involved, only the current state of the field and the charge at that point. The sign of the charge matters here. Positive and negative charges respond in opposite ways. Place them in the same field, and they accelerate in opposite directions. This is not because the field changes, it is because charge defines how the particle interprets the field structure. This interpretation happens continuously. As a charged particle moves, it also reshapes the field. That reshaping then feeds back into how other charged particles respond. Motion and interaction are never separate. They are two sides of the same field-based process. What makes this especially striking is how universal the response is. Every electron responds to electromagnetic fields in exactly the same way. No matter where it is, no matter how it was created, no matter how long it has existed, the charge guarantees identical behavior. This universality is why we can make precise predictions. Particle accelerators work because charge behaves consistently. Circuits function because electrons respond reliably. Even light interacting with matter depends on how charges shift and rearrange under fields. Charge does not tell a particle where to go. It tells it how strongly it must respond when a field is present. The field provides direction. Charge provides sensitivity. Together, they determine motion. There is a subtle point here. The particle does not carry instructions about every possible field it might encounter. It carries only its charge. The rest of the behavior emerges dynamically as the field and particle meet. This keeps the laws of physics local and economical. Seen this way, charge is not passive. It is an active interface between matter and the electromagnetic structure of space. It is how particles listen to fields and how fields register the presence of particles. This brings us to another important realization. If charge determines response, and many particles share the same charge, then very different particles can behave identically in electromagnetic situations. Understanding why that happens leads us to the next step: why different particles can carry the same charge value at all. Once charge is understood as a way of responding to the electromagnetic field, it becomes less surprising that very different particles can share the same charge. What matters is not their mass, size, or internal complexity. What matters is how their fields participate in the same symmetry. An electron and a muon, for example, are not the same particle. The muon is heavier, it is unstable, it decays quickly. Yet when placed in an electromagnetic field, it behaves just like an electron with the same charge. It curves the same way. It accelerates the same way. The field does not care about the differences. This is because charge does not describe the particle as a whole. It describes only one aspect of how its field transforms under the electromagnetic symmetry. If two different fields transform in the same way, they must couple with the same strength. The charge comes out identical. From the field perspective, this is natural. Fields can differ in many properties while still sharing the same interaction rules. One field may produce a heavy particle, another may produce a light one. But if both are required to respond to the electromagnetic field in the same way, their charge must match exactly. This is why charge feels almost detached from the rest of a particle's personality. Spin can differ, mass can differ, lifetime can differ. Charge often remains the same. It is not a summary of the particle, it is a specific commitment to a symmetry. This also explains why charge comes in families. Many particles share the same basic charge values. They fall into patterns. These patterns are not coincidences, they reflect how different fields are organized under the same underlying rules. Importantly, this sharing does not dilute charge. One particle having a certain charge does not weaken it for another. Each field carries its own coupling. The electromagnetic field interacts with all of them independently and locally. This reinforces the idea that charge is not a resource that must be divided. It is not a finite supply. It is a consistent relationship. Many participants can share the same rule without exhausting it. There is a deeper elegance here. The universe does not need to invent a new interaction rule for every particle. It reuses the same symmetry. Fields that obey it inherit the same charge behavior. Complexity grows without chaos. Seen this way, charge becomes a unifying feature rather than a distinguishing one. It groups particles into shared modes of interaction. It tells us not what a particle is made of, but how it is allowed to engage with one of the fundamental structures of reality. And this naturally raises another contrast. If charge is shared so freely and mass varies so widely, then these two properties must be very different in nature. Understanding that difference will sharpen the answer to our original question even further. At this point, charge invites comparison with mass, because the two often appear side by side in our descriptions of particles. Yet, at the quantum level, they arise from very different origins and play very different roles. Charge determines how a particle interacts with the electromagnetic field. Mass determines how a particle responds to motion and inertia. One governs interaction, the other governs resistance to change. They are not variations of the same idea. They answer different questions. Mass, in modern physics, is tied to how particles interact with the Higgs field. A particle's mass reflects how strongly it couples to that field. Change the coupling, and the mass changes. This is why particles span such a wide range of masses. The couplings differ. Charge behaves differently. It does not vary continuously. It does not arise from adjustable strength in the same way. A particle either couples to the electromagnetic field in a specific allowed manner, or it does not. The charge comes out fixed. This difference has consequences. Mass can change under extreme conditions. Particles can gain effective mass inside materials. They can behave as if they are heavier or lighter depending on their environment. Charge does not do this. An electron does not become slightly less charged inside a solid. Its interaction strength remains exact. There is also a difference in how these properties influence space. Mass curves space-time itself through gravity. Charge reshapes the electromagnetic field. One alters geometry, the other alters field configuration. They operate through distinct channels. Because of this, mass can be screened or hidden. Inside certain materials, collective effect can reduce how mass appears to behave. Charge cannot be screened in the same fundamental way. Fields can rearrange to neutralize large regions, but the individual charges remain intact. This distinction sharpens the original question. If charge were made of something, we might expect it to behave more like mass. Variable, context-dependent, but it does not. Its rigidity points back to symmetry rather than substance. Charge feels less like a quantity accumulated through interaction, and more like a statement about identity. Mass answers how hard it is to move something. Charge answers whether and how it must respond to a specific field. Seen this way, charge is closer to a rule than a measure. It is not something that builds up gradually. It is something that defines participation from the start, and this prepares us for the next step. If mass and charge behave so differently, what happens to charge when particles themselves appear and disappear? When matter is created or annihilated? Following charge through those processes will reveal just how deeply it is woven into the structure of quantum reality. When particles are created or destroyed, charge reveals how deeply constrained it truly is. At first glance, these events seem dramatic. Particles appear from energy. Others vanish completely. Matter turns into radiation. Yet through all of this, charge behaves with calm precision. In particle creation, charge never appears alone. When a charged particle is produced, another particle with the opposite charge must appear at the same time. An electron is never born without a partner. A positron emerges with it. The charges balance instantly and exactly. This is not a tendency. It is a requirement. The symmetry that gives rise to charge does not allow net charge to emerge from nothing. Energy can convert into particles, but it must do so in a way that preserves charge perfectly. Annihilation follows the same logic in reverse. When an electron meets a positron, both particles disappear. What remains is energy, often in the form of photons. Yet charge does not vanish. The opposite charges cancel each other precisely, leaving a neutral outcome. What is striking is how indifferent charge is to the drama of the event. From the perspective of charge, nothing special has happened. The accounting balances. The symmetry is preserved. The universe remains consistent. This behavior shows that charge is not tied to the persistence of matter. Particles can come and go. Charge is not attached to their longevity. It is attached to the structure of interactions themselves. As long as the symmetry holds, charge flows through processes without loss. Even in the early universe, when particles were being created and destroyed constantly, charge conservation held. The universe did not drift into imbalance. Matter and antimatter emerged in paired structures. The electromagnetic symmetry enforced order amid chaos. This also explains why exotic processes do not surprise physicists. When new particles are proposed, their charges are not guessed freely. They are dictated. The theory demands which charges are allowed and how they must balance in every interaction. Charge behaves almost like a thread that weaves through events without being consumed by them. It does not belong to any single particle. It passes through creation, interaction, and annihilation unchanged. Seen this way, asking what charge is made of feels less useful than asking what charge survives. It survives everything particles do. It survives energy transformations. It survives the disappearance of the very carriers we associate it with. This resilience points back to the same conclusion again and again. Charge is not a substance that particles own. It is a rule that processes obey. It is preserved not because something protects it, but because the universe cannot function without that preservation. And yet, one question remains open. If charge is so fundamental, so rule-based, why does it have the value it does? Why this coupling strength and not another? Physics has not fully answered that. Exploring that edge of knowledge brings us to the next and final frontier of this question. After everything we understand about charge, one question remains gently unresolved. Why does charge have the value it does? Why this precise coupling strength and not another? Physics can describe charge with extraordinary accuracy. It can predict how it behaves, how it flows, how it shapes matter and light. But when it comes to explaining why the electromagnetic coupling has its specific numerical value, the theory becomes quiet. This silence is not a failure. It marks the edge of current understanding. In quantum field theory, the value of the electric charge is an input. It is measured, not derived. The theory tells us what happens given that value. It does not yet tell us why that value exists. This can feel unsettling. We often hope that deeper theories will explain everything, yet here, depth reveals a boundary. Charge exists because symmetry requires it. Its conservation follows from that symmetry. Its behavior is dictated precisely, but its strength appears as a fundamental constant. There are ideas that gesture beyond this boundary. Some theories suggest that charge might be determined by deeper unifying principles. Others explore whether the value could emerge from conditions in the early universe. There are even proposals where multiple possible values exist across different regions, with ours being one that allows stable matter. None of these ideas are settled. They remain active areas of research rather than conclusions. What matters is how carefully physics treats this uncertainty. The question is not ignored. It is held open. Interestingly, the value of charge is just right for complexity. If it were much stronger, electrons would cling too tightly to nuclei. Chemistry would collapse into rigidity. If it were much weaker, atoms would barely hold together. Structure would struggle to form. This balance can feel suggestive, but physics resists turning suggestion into story. Instead, it notes the fact and continues working. The universe behaves this way. The task is to understand how before asking why. There is something instructive here. Charge teaches us that explanation does not always mean reduction. Sometimes it means recognizing which questions are answered by structure and which remain as foundations. Charge is not unexplained in its behavior. It is unexplained only in its value. And that distinction matters. We know what charge is. We know how it operates. We know why it must exist. What we do not yet know is why the universe chose this particular strength for its interaction. This open edge is not a gap in knowledge so much as a horizon. It reminds us that physics is not finished. There are deeper layers still to explore. Perhaps future theories will connect charge to something even more fundamental. Perhaps they will not. Either way, charge stands as a reminder that the universe is not arbitrary, but neither is it fully transparent. Some features are given, others are derived. Learning to tell the difference is part of understanding what it means to say something is fundamental. And with that recognition, we are ready for the final step. Not another open question, but a clarification. What it truly means, in modern physics, to say that charge is fundamental at all. When physics calls charge fundamental, it is making a precise statement. It is not saying charge is mysterious or beyond understanding. It is saying that charge sits at the bottom of an explanatory chain. Other behaviors depend on it. It does not depend on anything simpler. In modern physics, a fundamental quantity is one that cannot be reduced to a mechanism beneath it without changing the theory itself. Charge meets this condition cleanly. It is not composed. It is not emergent from smaller parts. It is defined by symmetry and enforced by the structure of quantum fields. This means charge is not discovered the way a hidden object is discovered. It is recognized the way a rule is recognized, through consistent behavior, through invariance, through the fact that every successful description of electromagnetic interaction requires it. Charge is fundamental because it is unavoidable. Remove it, and the electromagnetic field cannot exist in its current form. Alter it arbitrarily, and the symmetry collapses. The theory stops working. Matter loses stability. Prediction fails. This is a different kind of fundamentality than substance. Charge is not fundamental because it is small or indivisible. It is fundamental because it defines a relationship that everything else must respect. In this sense, charge is closer to geometry than to matter. Geometry is not made of parts. It is a framework that shapes motion and possibility. Charge plays a similar role for electromagnetic interaction. It defines how fields and particles are allowed to meet. This perspective also clarifies why the question, "What is charge made of?" slowly dissolves as understanding deepens. The question assumes that everything must be assembled. Physics shows that some things are stipulated, they are not built. They are declared by symmetry and upheld by consistency. Charge does not sit inside particles like an ingredient. It sits in the rules that allow particles to exist as they do. Particles are expressions of fields. Fields obey symmetries. Charge is one of the consequences of those symmetries being enforced everywhere and always. Once this is seen, the behavior of charge no longer feels strange. Its indivisibility makes sense. Its conservation is inevitable. Its identical value across identical particles becomes obvious. These are not features that need protection. They are features that cannot be otherwise. So what is charge made of according to quantum physics? It is not made of anything. It is a measure of how strongly a field must respond. It is a permission written into the structure of reality. It is a number that encodes a rule. This does not diminish it, it elevates it. Charge is not less real because it is not material. It is more deeply real because matter must obey it. And this is where the journey naturally pauses, not with a conclusion, but with a settled understanding. Charge is not hidden substance waiting to be uncovered. It is a foundational feature of how the universe organizes interaction. A quiet constant that shapes everything from atoms to light, simply by being what it is. Once charge is understood as fundamental, another layer quietly comes into view. Charge does not just enable interactions, it also forbids many others. It acts as a constraint on what can and cannot happen in the universe. Certain interactions are simply impossible because of charge. A charged particle cannot suddenly ignore an electromagnetic field. Two like charges cannot decide to attract instead of repel. These are not tendencies, they are restrictions enforced by the structure of the theory. This is an important shift in perspective. We often think of physical laws as describing what happens. Charge also tells us what is not allowed to happen. It closes doors as firmly as it opens them. Because of charge, matter organizes into specific patterns. Electrons cannot collapse freely into nuclei. Atoms cannot lose their structure without extreme conditions. Large-scale electrical imbalances cannot persist for long. The universe is steered away from chaos by the constraints charge imposes. This is why charge feels so reliable. It does not merely influence outcomes, it limits the space of possible outcomes. The universe explores only the paths that respect charge and ignores all others completely. Seen this way, charge is not just a participant in physics, it is part of the rule set that defines the game itself. And this realization prepares us for another deepening question. If charge constrains interaction so strongly, how does it shape the large-scale behavior of matter and energy over time? Once charge is understood as a constraint, its influence begins to feel much larger than individual particles. Charge does not merely act at microscopic distances, it quietly organizes matter across enormous scales, simply by limiting which arrangements are allowed to persist. Consider how quickly large imbalances of charge disappear. In everyday conditions, it is almost impossible to keep regions of strong net charge separated for long. Electrons move, currents flow, fields rearrange. The universe seems eager to return to electrical balance. This is not preference, it is enforcement. Configurations with large net charge store enormous energy in the electromagnetic field, and the field responds by driving matter to redistribute. This behavior explains why most objects around us are electrically neutral, not because charge is rare, but because neutrality is stable. Positive and negative charges find one another and settle into arrangements where their fields cancel at large distances. Matter organizes itself into atoms, molecules, and solids because those structures minimize electromagnetic tension. At the scale of atoms, charge dictates architecture. The nucleus carries positive charge. Electrons carry negative charge. The electromagnetic field allows only certain standing patterns of responsiveness between them. Those patterns become atomic orbitals. Chemistry follows from how these patterns overlap and rearrange. At larger scales, the same rules persist. In plasmas, where charges are free to move, electromagnetic forces dominate behavior. Filaments form, currents twist into ropes. Vast structures emerge in space, shaped not by gravity alone, but by charged particles interacting through fields that stretch across light years. Even stars are organized by charge in subtle ways. While gravity drives their overall structure, electromagnetic interactions govern how energy moves inside them. Charged particles scatter light. Fields guide flows. Charge quietly regulates how matter and radiation exchange energy. This influence is so pervasive that it often goes unnoticed. Gravity feels dramatic because it shapes planets and galaxies. Charge works more intimately. It shapes matter itself. It determines whether solid objects exist, whether light can be absorbed, whether stable temperatures are possible. What is striking is that none of this requires charge to act intelligently. There is no planning, no adjustment. The constraints alone are enough. By forbidding certain configurations and allowing others, charge steers the universe into structured complexity. This brings us back to the earlier idea that charge is not a thing but a rule. Rules do not push, they restrict, and through restriction, they create form. Just as the rules of geometry determine which shapes can exist, charge determines which arrangements of matter can survive. There is also a temporal aspect to this. Charge does not only organize space, it organizes time. Electrical processes have characteristic rates. Currents flow at certain speeds. Fields adjust on precise timescales. These rates set the rhythm of many physical systems. Signals in nerves depend on charge movement. Chemical reactions depend on charge rearrangement. Electronic devices function because charge responds predictably over time. The regularity of these processes is a direct reflection of the rigidity of the underlying rules. If charge were less constrained, time itself would feel different. Processes would drift, responses would vary, reliability would erode. The predictability we experience in physical systems depends on charge being exact, conserved, and universal. This universality is especially important. The same charge rules apply everywhere, in distant galaxies, in the early universe, in extreme environments where temperatures and densities are far beyond anything we can produce. Charge does not weaken with age or distance. It does not adapt to context. Because of this, the universe can build complexity on top of itself. Structures formed early remain compatible with structures formed later. Physics does not have to renegotiate its rules as conditions change. Charge provides a stable backbone. At this point, the original question feels very far away. What is charge made of? The answer no longer feels like it should involve ingredients. Charge behaves more like a boundary condition, a fixed constraint that everything else must satisfy. And yet, there is one more subtlety worth returning to. Charge does not exist alone. It exists alongside other fundamental constraints. Spin, statistics, other symmetries. Understanding charge fully means understanding how it fits into this wider network of rules that jointly define what reality can be. This opens a natural next direction, how charge interacts with other quantum properties to produce the full behavior of particles and fields, not as isolated features, but as interlocking constraints that together shape the universe. Once charge is seen as a constraint on interaction, it becomes impossible to treat it in isolation. Charge does not act alone. It operates alongside other quantum properties, and the stability of matter emerges only from their combined effect. One of the most important of these properties is spin. Spin is not rotation in space. It is an intrinsic feature of particles that determines how they behave under symmetry and how they can be arranged. Electrons, for example, all have the same spin value. This simple fact has enormous consequences. Electrons are also subject to quantum statistics. They obey a rule called the exclusion principle. No two electrons can occupy the same quantum state at the same time. This rule is not negotiable. It is enforced everywhere, always. Charge enters this picture quietly but decisively. The electromagnetic attraction between electrons and nuclei pulls electrons inward. Left. Alone, this attraction would allow electrons to collapse into the lowest possible state, piling endlessly into the same configuration. Atoms would shrink. Matter would lose structure. Spin and statistics prevent that collapse. The exclusion principle forces electrons to spread out into distinct states. Charge provides the attraction. Spin and statistics provide the resistance. Stability emerges from their tension. This balance is delicate and exact. The electromagnetic force is strong enough to bind electrons to nuclei, but not so strong that it overwhelms the restrictions imposed by quantum statistics. The result is atoms with size, shape, and internal structure. This is not an accident. If charge were stronger, the electromagnetic pull would overpower the exclusion principle. Atoms would be smaller and denser. Chemistry would be drastically altered. If charge were weaker, electrons would drift farther out. Bonds would weaken. Complex molecules would struggle to form. Spin alone cannot stabilize matter. Statistics alone cannot bind it. Charge alone cannot structure it. Only together do they produce a universe with solids, liquids, and gases, with stars and planets, with long-lived structures. This cooperation also explains why matter resists compression. When you press on a solid object, you are not pushing against empty space. You are pushing electrons closer together. Charge pulls them toward nuclei. Statistics push back by forbidding overlap. The resistance you feel is quantum mechanical at its core. Even pressure inside stars reflects this balance. In white dwarf stars, matter is compressed so intensely that electron statistics provide the primary resistance against gravitational collapse. Charge still binds electrons to nuclei. Spin and statistics dictate how tightly they can be packed. Entire stellar lifetimes depend on this interplay. What is remarkable is how cleanly these rules combine. There is no confusion, no ambiguity. Each property plays its role without overlap. Charge determines interaction with the electromagnetic field. Spin determines symmetry behavior. Statistics determine occupancy. Together, they define what matter can be. This also clarifies why charge feels so foundational. It participates in nearly every stabilizing process without dominating them. It is neither overwhelming nor negligible. It sets the stage on which other constraints can act. Seen this way, charge is not just a property of particles. It is part of a coordinated system of rules that jointly limit reality. Remove one rule, and the system fails. Keep them all, and complexity becomes possible. This perspective deepens the meaning of fundamentality. Charge is fundamental not because it explains everything alone, but because nothing works without it. It is one of the irreducible commitments the universe makes. Returning again to the original question, what is charge made of? the answer becomes even quieter. Charge is made of consistency with other rules. It exists because it fits, because it can coexist with spin, statistics, and symmetry in a way that produces a stable universe. What began as a question about composition slowly revealed itself as a question about structure. We asked what charge is made of, expecting perhaps layers or ingredients, and instead found rules, constraints, and relationships that cannot be taken apart without unmaking the picture entirely. Charge does not sit inside particles like a hidden substance. It does not accumulate or erode. It does not fragment or dissolve. It exists as a fixed way of participating in the electromagnetic field, enforced everywhere by symmetry and preserved through every process the universe allows. Seen this way, charge is less like matter and more like grammar. It does not describe what something is, but how it is allowed to behave. It determines how fields respond, how particles move, how matter organizes, and how light interacts with the world. Remove it, and the sentences of physics no longer make sense. What is most striking is how quietly charge does its work. It does not announce itself. It does not require attention. Yet every stable structure depends on it. Atoms hold together because charge demands balance. Chemistry unfolds because charge fixes interaction strength. The solidity of objects, the flow of currents, the existence of light as we experience it, all trace back to this single, exact rule. In modern physics, calling charge fundamental is not an admission of mystery. It is a recognition of completion. We know where charge comes from in the structure of theory. We know how it behaves. We know why it is conserved and why it cannot vary. What remains open is not its nature, but its ultimate origin, why this particular rule and not another was chosen. And perhaps that is enough. Not every foundation needs a deeper foundation beneath it. Some features of reality are not assembled. They are declared by the way the universe holds itself together. So when the question returns one last time, what is charge made of according to quantum physics? The answer is calm and spare. Charge is made of symmetry, of consistency, of rules that allow interaction to exist at all. It is not hidden inside matter. It is written into how matter and fields are allowed to meet. And once that is seen clearly, the question no longer presses for resolution. It settles. The universe does not explain charge further, because it does not need to. Charge is already doing exactly what it must, everywhere, without exception.